History of neural networks. Understanding the history of neural networks is crucial to appreciate their current applications and future potential. This history begins in the 1940s and encompasses several key developments and concepts. To visualize this timeline, we will create a simple Python code snippet that plots major milestones. The provided Python code generates a simple timeline highlighting key milestones in the history of neural networks. It uses matplotlib for plotting, where years are mapped along the x-axis and significant events are labeled appropriately. This visual representation starts from the formulation of the McCulloch-Pitts neuron model in 1943, coming up to the development of AlexNet in 2012, showcasing the evolution from simple models to complex deep learning architectures. This timeline serves as a concise summary of how far neural networks have come, emphasizing periods of intense research activity and significant technological breakthroughs. Importance and applications of neural networks. Neural networks, a core technology behind artificial intelligence, AI, have transformed how we interact with technology and data. By mimicking the neural structures of the human brain, they enable computers to learn and make decisions in a way that's analogous to human thinking. This powerful capability finds utility in a broad spectrum of applications, from everyday tools to complex scientific research. In the provided code snippet, we leverage sklearn.neural networks (MLP) classifier to create a simple neural network model. This model uses a dataset, x of y for target labels, to learn and adjust its parameters. It's configured with LBFGS solver and a hidden layer structure of 5-2, demonstrating how neural networks can be easily implemented and trained on datasets for classification tasks. This is just one facet of their vast applications, which include image and speech recognition, medical diagnosis, stock market trading prediction, and many forms of automation and predictive analysis. The ease of such implementations underscores the significance of neural networks in developing intelligent systems. Basic structure of neural networks. Neural networks are inspired by the structure of the human brain. At a high level, they consist of an input layer, one or more hidden layers, and an output layer. Each layer is made up of nodes or neurons, which are connected by links. Each link has an associated weight, and each node applies an activation function to its net input, the weighted sum of its inputs, to generate an output. Let's define a simple neural network structure in Python using lists and NumPy. The provided code defines a function, initializeNetwork, that initializes a simple feed-forward neural network with a specified number of input, hidden, and output neurons. It uses NumPy to generate random weights for each connection. Each neuron in a layer, excluding the input layer, is represented as a dictionary containing a weights key with a list of weights, where the extra weight is the bias term. The network is created as a list of layers, where each layer is a list of neurons. The initializeNetwork function takes 3 arguments: n inputs for the number of inputs, n hidden for the number of neurons in the hidden layer, and n outputs for the number of output neurons. This function demonstrates how to set up the basic structure of a neural network, but does not include the implementation of forward propagation or training algorithms. Types of neural networks: feed-forward, recurrent, convolutional. Neural networks are a subset of machine learning and form the backbone of deep learning algorithms. Their design is inspired by the human brain's architecture, and they're formulated to recognize patterns from complex data. There are principally 3 types of neural networks, each with unique architectures and applications. Feed-forward neural networks, FNN, are the simplest type of artificial neural network architecture. In this network, the information moves in only one direction, forward, from the input nodes through the hidden layers, if any, and to the output nodes. There are no cycles or loops in the network. Recurrent neural networks, RNN, introduce loops within the network, allowing information to be persisted. This architecture is well suited for sequential data like time series or natural language processing, as it can maintain a memory of previous inputs in the network's internal state. Convolutional neural networks, CNN, are specifically designed for processing grid-shaped data such as images. Convolutional layers in these networks can capture spatial hierarchy in input data, making them powerful for tasks like image recognition, video analysis, and even playing games. Each of these networks serves different purposes and is chosen based on the specifics of the problem at hand. Introduction to deep learning. Deep learning is a subset of machine learning, focusing on algorithms inspired by the structure and function of the brain, called artificial neural networks. The simplest deep learning models are based on layers of neurons, where each neuron learns to transform its input data into a slightly more abstract and composite representation. Let's explore a very basic example using Python's popular deep learning library, Keras, to illustrate how a simple neural network can be constructed. In the provided code snippet, we start by importing sequential from keras.models, which allows us to create a linear stack of network layers. We also import dense, a fully connected neural network layer from keras.layers. We then define our model using the sequential model type, which is a simple stack of layers. The first layer is a dense layer with 32 neurons and uses the ReLU, rectified linear unit activation function. This layer expects input with a shape of 784, which means it expects 784 dimensional vectors. The second dense layer has 10 neurons and uses the softmax activation function, which is often used for multi-class classification problems. After defining the layers, we compile the model using the Adam optimizer and the categorical cross-entropy loss function, which is common for classification tasks. Finally, we print a summary of the model to get an overview of its architecture, including the number of parameters at each layer, linear algebra, vectors, matrices. In the context of neural networks, understanding vectors and matrices is crucial because they are the foundation of how data is represented and manipulated within a network. Vectors can be thought of as lists of numbers, and matrices are essentially tables made up of vectors that are organized in rows and columns. Operations involving vectors and matrices, such as addition, multiplication, and scalar operations, are fundamental in performing computations in neural networks. The code begins by importing the NumPy library, which is a fundamental package for scientific computing in Python. It provides support for arrays, which are used to create vectors and matrices. The vector is created using np.array123, representing a simple list of numbers. Meanwhile, the matrix is formed using np.array123, 4, 5, 6, 7, 8, 9, which constructs a 3x3 table of numbers. Each nested list within the matrix represents a row. Lastly, both the vector and the matrix are printed to display their structures. This introduction illustrates how vectors and matrices can be easily constructed and manipulated using NumPy, making it an invaluable tool for neural network implementations. Differential calculus, derivatives and gradients. Differential calculus focuses on the concept of change and rates of change, which are essential in understanding how to optimize neural network models. The derivative of a function at a point gives the slope of the tangent line to the function at that point, indicating the rate of change. When we move to functions of multiple variables, the gradient extends this concept by providing a vector of partial derivatives, each representing the rate of change with respect to a different variable. In the code, we first define a simple univariate function, f of x equals xq, and calculate its derivative df dx equals 2x at x equals 4, which gives us the rate at which f changes with x at that point. The result, df dx, shows a rapid increase since the slope is positive and steep for larger values of x. Next, for a function of two variables fxy equals x2 plus y2, we calculate the gradient as an array 2x, 2 more y at the point 3, 4. This gradient vector shows how the function changes with respect to both x and y. Gradients are foundational in training neural networks, as they guide how model parameters should be adjusted to minimize the loss function. Probability theory and statistics. Understanding the basics of probability theory and statistics is crucial for neural networks, as it helps in modeling uncertainty, making predictions, and interpreting the behavior of the network. In this example, we'll illustrate how to calculate basic descriptive statistics using Python, which are fundamental in data analysis for neural networks. This code snippet demonstrates the calculation of 4 fundamental descriptive statistics in data analysis: mean, median, variance, and standard deviation, using NumPy's methods. The mean gives the average value, indicating the central tendency. The median represents the middle value when the data is ordered, which is less affected by outliers. The variance measures the data's spread from the mean, illustrating the degree of variation. Lastly, the standard deviation is the square root of the variance, offering a measure of dispersion that is in the same units as the data. These statistics are the building blocks of probabilistic and statistical analysis in neural network data preparation and evaluation. Optimization basics, cost functions, gradients, backpropagation. Optimization in neural networks involves finding the best parameters, weights and biases, that minimize the cost function. The cost function measures the difference between the network's prediction and the actual target values for the training data. Gradients represent the direction and rate at which the function's value changes, guiding the optimization process. Backpropagation is a method to efficiently compute these gradients. In the provided code, we define a simple cost function named compute cost, which calculates the mean squared error, MSE, between the predicted values, ypred, and true values, ytrue, of a dataset. The MSE is calculated as the sum of the squared differences between each corresponding true and predicted value, averaged over the number of examples m. This cost function is essential in optimization as it quantifies the error of the model's predictions. Optimizing a neural network involves adjusting its parameters to minimize this error, guiding the model to better performance. The example usage demonstrates how to calculate the cost for a given prediction and true values, providing a straightforward example of how a cost function works in the context of neural network training. Neurons and how they work. In the context of neural networks, a neuron is a basic unit that receives input, processes it, and produces output based on the input and its activation function. The process can be summarized by the formula: output equals activation function, weighted sum of inputs plus bias. Let's simulate a simple neuron with a sigmoid activation function in Python. This code demonstrates how a simple artificial neuron operates. Firstly, sigmoid is defined as the activation function, transforming its input to a value between 0 and 1, making it useful for binary classification. The neuron receives inputs as an array, each associated with a weight reflecting its importance. Weights modify the inputs, and bias adjusts the output independent of the input value, acting like a threshold. mp. Calculates the weighted sum of inputs and weights. Finally, the activation function is applied to this sum, resulting in the neuron's output. This process mirrors biological neuron functions, enabling artificial neurons to make decisions by evaluating their inputs. Activation functions, ReLU, sigmoid, tant. Activation functions are crucial in neural networks as they decide whether a neuron should be activated or not. These functions introduce non-linearity, enabling the model to learn complex patterns. We'll explore three primary activation functions: ReLU, rectified linear unit, sigmoid, and tant, hyperbolic tangent. The code snippet defines and demonstrates three commonly used activation functions: ReLU, sigmoid, and tant, applied to an array of input values. ReLU activates only positive inputs, keeping negatives at 0, making it efficient but potentially prone to dying neurons in some cases. Sigmoid outputs between 0 and 1, making it suitable for binary classification tasks but susceptible to vanishing gradients. Tan, similar to the sigmoid but outputs range from -1 to 1, offers a zero-centered output, which can make training converge faster in some cases. These functions are the building blocks for many neural network architectures, influencing the network's ability to learn and make complex decisions. Cost functions, mean squared error, cross entropy. Cost functions are vital in neural networks as they quantify the difference between the predicted outputs and the actual target values. Two common cost functions are mean squared error, MSE, and cross entropy. MSE is typically used for regression tasks, measuring the average of the squares of the errors. Cross entropy is preferred for classification tasks, quantifying the difference between two probability distributions, the predicted probabilities and the actual distribution. In the provided code, two functions are defined using Python and NumPy: MSE for calculating mean squared error and cross entropy for cross entropy. The MSE function computes the mean of squared differences between actual y-true and predicted y-pred values suitable for regression. The cross-entropy function calculates the negative sum of the actual values times the log of predicted probabilities, adjusted by a small value, 1e9, to prevent log 0, suitable for classification tasks. Both functions average the losses over all samples, yielding a single scalar value representing the cost. Gradient descent and its variance, SGD, ADAM, RMS prop. In neural networks, gradient descent and its variance, stochastic gradient descent, SGD, ADAM, RMS prop, are optimization algorithms used for minimizing the loss function, which is indicative of the difference between the actual and predicted outputs. These algorithms iteratively adjust the weights of the network to minimize this loss, improving the model's predictions. We'll delve into the basic Python implementation of these algorithms and contrast their approaches. The provided code snippet demonstrates a basic implementation of gradient descent, focusing on linear regression for simplicity. Here, we aim to find the best fit line by adjusting the slope m and y-intercept b to minimize the difference between the actual y and predicted outputs. The algorithm iteratively updates m and b based on the gradient of the loss function with respect to each parameter, multiplied by a learning rate, LR. This process is repeated for a fixed number of iterations. While not directly implementing SGD, ADAM, or RMS prop, this example establishes the foundational concept of adjusting parameters in the direction that minimally reduces error, which is common across all these variants. Each variant adjusts this basic approach to be more effective in different scenarios, such as handling noisy gradients or accelerating convergence. Backpropagation algorithm. The backpropagation algorithm is a cornerstone of neural network training. It's used to minimize the error in predictions by adjusting the weights of the connections in the network. This method involves two main phases: a forward pass to compute the output and an error, and a backward pass to propagate the error through the network and update the weights. Here, we'll illustrate a basic implementation of backpropagation for a simple neural network. In this code, we start by importing NumPy for handling arrays and matrix operations. The sigmoid function and its derivative are defined for use as the activation function, crucial for adding nonlinearity in the model. The neural network class initializes with random weights and contains methods feedForward and backprop. FeedForward computes the output of the network for given inputs, and backprop calculates the gradients using the derivative of the error with respect to the weights, and updates the weights based on these gradients to reduce the error. Here, simple two-layer neural structure is created, and the training process involves iteratively running these methods on example data, x, y, for a specified number of epochs, 1500 in this case, to adjust the weights, aiming for minimization of the output error. The adjustments are done through gradient descent, illustrated in the backprop method via the calculation and application of dweights1 and dweights2. Initializing weights. When creating a neural network, one crucial step is initializing the weights of the connections between neurons. Proper initialization helps in faster convergence of the network during training and can prevent issues related to vanishing or exploding gradients. There are multiple strategies to initialize weights, such as zeros, random, Xavier-Glorot initialization, and He initialization. This code snippet demonstrates how to initialize weights using the Xavier-Glorot initialization method for a layer in a neural network. This strategy is particularly suited for layers followed by a sigmoid or tanh activation function. It considers both the number of input units fan-in and output units fan-out to the layer, ensuring the weights are initialized with variance scaled according to the sum of fan-in and fan-out. The mp.random.randn function generates random numbers from a normal distribution, which are then scaled by mp.sqrt2 /fan-in plus fan-out, aligning with the Xavier initialization recommendation. This approach helps maintain the gradient scale and control, aiding in efficient learning. Data loading and preprocessing. Data loading and preprocessing are crucial steps in preparing your dataset for training neural networks. The first step involves loading the data in a manageable form, often as tensors. Pre-processing then involves transforming this data to a more suitable form, such as normalizing or standardizing, to make the training process smoother and more efficient. In this example, we import necessary modules from TorchVision for data loading and pre-processing. The transforms.compose is used to chain together two pre-processing steps. Transforms.toTensor converts images to PyTorch tensors, and transforms.normalize, point 5, normalizes the pixel values of the images. The mean and standard deviation values in the normalized transform are dataset specific and must be determined beforehand. We then load the MNIST dataset, applying the defined transform. Finally, Data Loader is used to iterate over the dataset in mini batches of size 64, with shuffling enabled to ensure the model gets different subsets of data during training. Model evaluation metrics: accuracy, precision, recall, F1 score. Model evaluation metrics are crucial for understanding the performance of your neural network model. Accuracy, precision, recall, and F1 score are standard metrics used to evaluate classification models. Let's explore these metrics with an example using Sklern's metrics module. Accuracy measures the proportion of true results, both true positives and true negatives, among the total number of cases examined. It's straightforward, but doesn't account for class imbalance. Precision measures the proportion of true positive results in the predicted positive cases, making it critical for scenarios where the cost of false positives is high. Recall measures the proportion of true positive results in the actual positive cases, important in cases like disease screening where missing a positive case, false negative, can be more detrimental than an incorrect positive prediction, false positive. F1 score is the harmonic mean of precision and recall, providing a balance between them, and is particularly useful when the class distribution is uneven. These metrics combined offer a comprehensive view of model performance, beyond what accuracy can provide alone. Overfitting, underfitting, and solutions, dropout, regularization. When training neural networks, achieving a fine balance so the model performs well on unseen data is crucial. Overfitting occurs when a model learns the training data too well, capturing noise and outliers, which harms its performance on new data. Underfitting, on the other hand, happens when the model is too simple to learn the underlying structure of the data. To mitigate these issues, techniques like dropout and regularization are used. In the provided code snippet, a simple neural network is created using the Keras library. It starts with a dense layer of 64 neurons, followed by a dropout layer set to drop out 50% of the neurons randomly during the training process to combat overfitting. Another dense layer of 64 neurons follows, leading to an output layer with 10 neurons and softmax activation function. The output layer also applies L2 regularization, penalizing large weights to further mitigate overfitting. This code exemplifies a practical approach to tackle overfitting through dropout and regularization in a neural network's architecture. Neural network architectures: fully connected layers, convolutional layers, recurrent layers. Understanding the different neural network architectures is crucial for designing models that are optimized for various tasks, such as image recognition, sequential data processing, or general pattern recognition. We'll explore three primary types: fully connected layers, convolutional layers, and recurrent layers. The code demonstrates the basic structure for three types of neural network architectures using TensorFlow. The fully connected layer model, designated as FC model, is a simple neural network with one input, one hidden, and one output layer, suitable for non-complex data patterns. The convolutional layer model, conv model, uses convolutional layers that are efficient for spatial data input like images, as they can capture spatial hierarchies in data. Lastly, the recurrent layer model, REC model, uses simple RNN layers suitable for sequential data, such as time series or text, as it can maintain information across inputs over time. Each of these architectures serves different purposes and is selected based on the task at hand. Introduction to CNNs. Convolutional neural networks, CNNs, revolutionized the field of computer vision by using specialized layers that automatically and efficiently learn spatial hierarchies of features from input images. Let's start by understanding the core components of CNNs, including convolutional layers and pooling layers. For simplicity, we'll use a small example with the Keras API in TensorFlow. In this code snippet, we create a simple CNN model using the sequential model from Keras. It starts with a convolutional layer, conv2D, that has 32 filters, each with a kernel size of 3 by 3, and uses the ReLU activation function. The input shape is set to 28-28-1, representing images of size 28 by 28 with a single color channel, e.g. grayscale images. Following the convolutional layer, we apply a max pooling layer, max pooling 2D, with a pool size of 2 by 2. This layer reduces the spatial dimensions, height and width of the input by taking the maximum value over a 2 by 2 pooling window. Finally, the model.summary call prints a summary of the model architecture, including layer types and their output shapes. Convolutional layer, pooling layers, and their functions. The convolutional layer is the core building block of a CNN. It applies a convolution operation to the input, passing the result to the next layer. This process helps the network learn image features such as edges, textures, and patterns. Here's a simple example of defining a convolutional layer in PyTorch. In this code, we import the necessary modules from PyTorch and define a convolutional layer using nn.convd. Here, in_channels=1 specifies that the input has one channel, e.g. a grayscale image. OutChannels=32 means the layer will produce 32 feature maps, and kernel size=3 indicates the size of the filter that will convolve over the input. Stride=1 sets the step size of the convolution, and padding=1 ensures the output size is the same as the input size by adding zeros around the input. CNN architectures: LeNet, AlexNet, VGG, ResNet. LeNet, developed by Jan LeCun in 1998, is one of the earliest CNN models designed for handwriting and character recognition. It contains convolutional layers, subsampling, average pooling layers, and fully connected layers. This code snippet outlines the architecture of the LeNet model using the Keras library. It starts with a convolutional layer with 6 filters of size 5 by 5, followed by an average pooling layer. This pattern is repeated with a second convolutional layer of 16 filters. Then, the model flattens the output and passes it through 3 fully connected layers, ending with a softmax layer for classification into 10 categories. TANT activation functions are used in line with the original model, except for the final layer, where softmax is applied for multi-class classification. Applications of CNNs: image recognition, video analysis, image generation. CNNs have revolutionized the field of computer vision by enabling machines to interpret and understand the visual world. We'll explore 3 key applications: image recognition, video analysis, and image generation, showcasing the versatility and power of CNNs. In this snippet, we leverage the VGG16 model, a pre-trained CNN from the Keras library optimized for image recognition to identify objects within images. The process involves loading an image, resizing it to match the model's input requirements, converting it to an array, and pre-processing it for VGG16. The model then predicts the contents of the image, and we display the top 3 predictions. This demonstrates CNN's role in image recognition by effectively classifying images into predefined categories. The adaptability of pre-trained models for rapid deployment across various domains exemplifies the applicability of CNNs beyond basic image recognition, including in video analysis, for frame-by-frame object detection, and image generation, through understanding and manipulating image features. Introduction to RNNs. Recurrent neural networks, RNNs, are a class of neural networks that are particularly useful for processing sequences of data, like time series or natural language. They are capable of maintaining a memory of previous inputs in their internal state, which allows them to exhibit dynamic temporal behavior. Unlike feed-forward neural networks, RNNs have connections that loop backwards, enabling them to process not just the current input, but also the information they have received previously. This Python code defines a simple RNN module using PyTorch, a popular deep learning library. The model, SimpleRNN, inherits from nn.module, which is a base class for all neural network modules in PyTorch. The constructor, init, initializes the RNN with sizes for the input, hidden, and output layers. It defines 2 linear layers, one I2H, translating the concatenated input and hidden state to the next hidden state, and another, I2O, translating the concatenated input and hidden state to the output. The forward method performs the forward pass of the RNN for a single time step, combining the current input with the previous hidden state, computing the next hidden state, and producing the output. The function init_hidden initializes the hidden state to zeros at the beginning of a sequence. This simple RNN can process inputs one time step at a time and maintain information across time steps through the hidden state. Problems with basic RNNs: vanishing and exploding gradients. To understand the challenges of vanishing and exploding gradients in basic RNNs, imagine a chain of computations getting longer with each time step. These issues arise due to the repeated multiplication of gradients through the network's depth, which corresponds to the sequence length in RNNs. In the provided code, we simulate the effect of gradient computations through a sequence of operations, which is a simplified representation of passing information through time steps in an RNN. The variable w represents a weight in the RNN, and we iteratively multiply this weight to simulate the process of gradients being passed back through time during backpropagation. If w is 1, the gradient diminishes as length increases, demonstrating the vanishing gradient problem. Conversely, if w hold 1, the gradient exponentially increases, illustrating the exploding gradient problem. These issues make training basic RNNs challenging, especially for long sequences, as the vanishing gradient makes learning long-term dependencies difficult, and exploding gradients can cause numerical instability. Long short-term memory, LSTM networks. Long short-term memory, LSTM networks are a type of RNN specialized in remembering information for an extended period. Unlike standard RNNs, LSTMs have a unique structure that allows them to avoid the vanishing gradient problem, making them effective for learning long-term dependencies. They introduce memory cells that can maintain information in memory for long periods and gates that control the flow of information. This code snippet demonstrates how to define a simple LSTM network using Keras. Firstly, we import the required modules. We create a sequential model, which is a linear stack of layers. We then add an LSTM layer with 50 units and ReLU activation function, indicating that this network input will have 100 time steps, each with one feature. Following the LSTM layer, a dense layer with a single unit is added for output. Finally, we compile the model with the Adams and Moore optimizer and mean squared error MSE loss function, making it suitable for regression problems. This structure is a basic example of how LSTMs are used in practice to model sequences. Gated recurrent units, GRUs. Gated recurrent units, GRUs, are a variant of RNNs that aim to solve the vanishing gradient problem by introducing gating mechanisms. These mechanisms allow the model to effectively capture dependencies for long sequences. A GRU has two gates, the update gate and the reset gate. The update gate helps the model to determine how much of the past information needs to be passed along to the future, and the reset gate decides how much of the past information to forget. In this code snippet, we first import necessary libraries from PyTorch. We define a GRU layer using torch.nn.gru with input size equals 10 and hidden size equals 20. This GRU layer is initialized to have a single layer num layers equals 1. The example input tensor input is created with dimensions seq_len batch input size, where seq_len equals 5, batch equals 3, and input size equals 10, simulating a batch of 3 sequences, each of length 5, and with each element in the sequence being a 10-dimensional vector. The initial hidden state, h0, is also specified, with dimensions corresponding to num layers num directions, batch, hidden size, in this case, 1, 3, 20. Finally, we perform a forward pass through the GRU using this input and initial hidden state, resulting in the output and the final hidden state hn. This demonstration shows how to instantiate and apply a GRU layer for a simple batch of sequences in PyTorch. Applications of RNNs, text generation, time series prediction. Text generation is a fascinating application of RNNs, where the network learns from a corpus of text and then generates new text that mimics the style and content of the original. Here, we will use a simple character-based RNN model to generate text. In this example, a character-based tokenizer is first used to convert the text into sequences of integers, where each unique character is assigned a unique integer. An embedding layer is then used to convert these integer sequences into dense vectors of fixed size, providing a way to input sequence data into the RNN. The LSTM layer, a variant of RNN, is crucial for capturing dependencies and relationships in sequential data. Finally, a dense layer with a softmax activation function is added to predict the next character given a sequence of characters. This model, once trained on a large corpus of text, can generate new text character by character. Generative Adversarial Networks, GANs. Generative Adversarial Networks, GANs, are a class of artificial intelligence algorithms used in unsupervised machine learning, implemented by a system of two neural networks contesting each other in a game, hence adversarial. They were introduced by Ian Goodfellow et al. In 2014. Essentially, one network generates candidates, generative, and the other evaluates them, discriminative. This process results in the generation of highly realistic data. The provided code initiates a basic setup for a generative adversarial network, GAN, using Keras. First, we start by constructing the generator model, which aims to generate new data points. The generator begins with a dense layer of 128 units, followed by a leaky Ryu activation function to introduce nonlinearity and combat the vanishing gradient problem. It then outputs data points in the desired shape. 784 units, for example, could represent a 28 by 28 pixel image if we're dealing with image data, using tant as the activation function. Next, the discriminator model is constructed to judge whether a given data point is real from the dataset or fake produced by the generator. It mirrors the generator structure, but ends in a single unit with a sigmoid activation function, classifying inputs as real or fake. Lastly, for training purposes, we compile the discriminator with binary cross-entropy loss and Adam optimizer. The non-trainability of the discriminator during the generator's training phase is crucial for stabilizing training, as it prevents the generator's gradients from affecting the discriminator directly. Then the GAN model is assembled by stacking the generator and discriminator, indicating that the generated data will be fed directly into the discriminator for evaluation. And it's compiled similarly. Autoencoders and variational autoencoders. Autoencoders are a type of artificial neural network used to learn efficient codings of unlabeled data. The network is designed to compress the input into a lower dimensional code and then reconstruct the output from this representation. This tutorial demonstrates a basic autoencoder that learns to compress and decompress images from the MNIST dataset. In this example, we first define the size of our encoded representations, choosing a dimension of 32. This means we are compressing the input, originally 784 floats for each MNIST image, into a 32-float representation, achieving a compression factor of 24.5. We start by defining our input placeholder, followed by the encoded representation of the input using a dense layer with Ryu activation. We then define the decoded representation, which aims to reconstruct the input from the encoded representation, using another dense layer, but this time with sigmoid activation for output. Finally, the model is set up to map an input to its reconstruction, creating a simple autoencoder. Reinforcement learning and deep Q networks, DQN. Reinforcement learning, RL, is a type of machine learning where an agent learns to make decisions by performing actions in an environment to achieve some goals. The agent receives rewards or penalties based on its actions, guiding it to learn the best strategy over time. Deep Q networks, DQN, combine RL with deep neural networks, where the Q network is trained to approximate the optimal action value function, representing the maximum expected return achievable by following any strategy after seeing a state and then taking an action. Let's look at a simplified example of implementing a DQN algorithm. This code snippet demonstrates the creation of a deep Q network, DQN, using TensorFlow. Initially, we import necessary libraries such as NumPy for numerical operations and TensorFlow for building and training neural networks. We then define our DQN model using TensorFlow's Keras API. The sequential model is chosen for its simplicity in stacking layers. Our DQN consists of 2 hidden layers, each with 24 neurons and ReLU activation functions, suitable for capturing the nonlinearities in the action value function approximation. The output layer has 2 neurons, assuming 2 possible actions in our simplified scenario, with linear activation, directly estimating the action values. The model uses mean squared error for loss and Adam optimizer for adjusting weights based on this loss, with a learning rate of 0.01, balancing the speed and stability of learning. Attention mechanisms and transformer models. Attention mechanisms dramatically improve the performance of neural network architectures on tasks that involve sequential data, such as natural language processing. They enable the model to focus on different parts of the input sequence while generating the output, mimicking the way humans pay attention to specific information when comprehending language or visual scenes. This code snippet defines a scaled dot product attention function, a core component of many attention mechanisms. The function takes queries Q, keys K, and values V as inputs, optionally along with a mask to ignore or prioritize certain parts of the input. The attention mechanism calculates the dot product of the query with all keys, scales it by the square root of the dimension of keys to prevent large values which can make softmax gradients very small, applies a softmax function to obtain the weights on the values, and finally computes a weighted sum of the values. If a mask is provided, e.g. for padding tokens not to affect the score, it's applied by adding a very negative value to the logits before softmax. This results in almost zero attention weights for those positions. Neural network optimization, hyperparameter tuning, neural architecture search. Neural network optimization focuses on improving the performance of neural networks. Two primary areas to explore in optimization are hyperparameter tuning, where we adjust the training parameters to improve model performance, and neural architecture search, NAS, which automates the search for the best neural network architecture. We'll look at a simple example involving hyperparameter tuning using grid search. The provided code snippet illustrates the process of hyperparameter tuning using grid search with Keras and scikit-learn's grid search CV. Initially, a Keras model creation function, createModel, is defined, which builds a simple sequential neural network for binary classification. The Keras classifier wrapper is then used to make this model compatible with scikit-learn utilities. The important part comes with defining param_grid, a dictionary that specifies batches to test for training, batch size, the number of training epochs, and optimizer types, optimizer. Grid search CV will then systematically experiment with all combinations, 3x3x2 or 18 in this case, and perform cross-validation to determine which combination yields the best model performance. This approach is straightforward for executing hyperparameter tuning, but can become computationally expensive with more parameters and larger data. Introduction to TensorFlow. TensorFlow is an open-source machine learning framework developed by Google. It is widely used for developing and training machine learning models, particularly deep neural networks. TensorFlow offers both a high-level API for quick prototyping and low-level APIs for fine control over model architectures. This makes it suitable for both beginners and advanced users. In this introduction, we will create a simple neural network in TensorFlow to classify images from the MNIST dataset, handwritten digits. This code performs several key steps in using TensorFlow to work with a neural network. Firstly, it imports the TensorFlow library. It then loads the MNIST dataset, which includes images of handwritten digits that the model will learn to classify. The dataset is split into training and test datasets. Data normalization is an important pre-processing step that is performed to ensure numerical stability during the learning process. The neural network model is constructed using TensorFlow's Keras API, employing a sequence of layers that includes a layer to flatten the input, a dense layer with 128 neurons, and ReLU activation function, a dropout layer to prevent overfitting, and a final dense layer for classification. The model is compiled with the Adam optimizer and a loss function suited for classification tasks. Training the model involves fitting it to the training data over a specified number of epochs. Finally, the trained model is evaluated on the test dataset to see how well it performs on unseen data. Introduction to PyTorch. PyTorch is an open-source machine learning library developed by Facebook's AI Research Lab. It provides flexibility and speed in building and training deep learning models. Below is a simple example of defining and initializing a neural network using PyTorch. In this example, the net class defines a simple convolutional neural network, CNN, for image classification. It inherits from nn.module, which is a base class for all neural network modules in PyTorch. The CNN consists of two convolutional layers, conv1 and conv2, followed by max pooling, pool, and three fully connected layers, FC1, FC2, FC3. The forward method defines how the data flows through the network, i.e., the network's architecture. When data passes through the network, it undergoes activation, ReLU, pooling operations, and is finally transformed by the fully connected layers. After defining the network class, an instance of the network, net, is created and printed, which shows the structure and layers of the model. This example highlights PyTorch's straightforward approach to model definition and manipulation. Model deployment, TensorFlow serving, ONNX. TensorFlow serving provides a flexible, high-performance serving system for machine learning models designed for production environments. It makes it easy to deploy new algorithms and experiments while staying the same server architecture and APIs. The following example shows how to use TensorFlow serving to serve a TensorFlow model. These commands first pull the TensorFlow serving Docker image, making it available on your machine. Then, a Docker container is run, exposing port 8501, which is TensorFlow serving's default port for REST API requests. The mount option is used to bind the directory containing your saved model to the container. This makes the model accessible to TensorFlow serving. The Nash eModel name flag sets the environment variable in the container, specifying the name of the model to serve. This setup is crucial for deploying and testing your TensorFlow models in a production-like environment, providing a RESTful API for model inference. Use of GPUs and TPUs in training. Training deep learning models can be extremely time-consuming due to the vast amount of computations required. To accelerate this process, GPUs, graphics processing units, and TPUs, tensor processing units, are commonly used. GPUs, originally designed for rendering graphics, are highly efficient at matrix operations and parallel processing, making them ideal for neural network computations. TPUs, on the other hand, are custom chips specifically designed to accelerate deep learning tasks. Here's how to configure TensorFlow to use a GPU. The code first imports the TensorFlow library, which is a popular framework for developing and training machine learning models. It then uses tf.config.list physical devices GPU to retrieve a list of available GPUs on the system. If a GPU is available, it prints a confirmation along with the GPU device details. If not, it informs the user that no GPU is available. This is a basic but essential step in configuring TensorFlow to leverage the power of GPUs for increased training speed and efficiency. It's important to ensure your TensorFlow installation is set up to support GPU usage, which may require additional drivers and libraries depending on your system. Neural network visualization tools, TensorBoard, Netron. TensorBoard is a visualization tool provided by TensorFlow that helps in understanding, debugging, and optimizing the model. It tracks various metrics such as loss and accuracy, visualizes the model graph, displays images, and more during the training process. Here's how to set it up for a TensorFlow model. In this code snippet, we import TensorBoard from the Keras callbacks. We create a log directory named log/fit, along with the current date and time for unique identification. The TensorBoard instance is then configured to log histograms every epoch using histogramFreq = 1. This setup is completed by including the TensorBoard callback in your model's fit method through the callbacks argument. This will allow TensorBoard to monitor the training process, which can be viewed by running TensorBoard in a terminal, pointing it to the log directory. Ethical considerations in AI: bias, privacy, security. Understanding the ethical considerations in AI, including bias, privacy, and security, is fundamental to building and deploying responsible artificial intelligence systems. The following example demonstrates a pseudocode for implementing a simple check to mitigate bias in a dataset before training a model. The provided pseudocode illustrates a basic approach to mitigate bias in a dataset, which is a crucial aspect of ethical AI. The function mitigate bias takes a dataset as input and applies a hypothetical function, balance dataset by sensitive attributes, to adjust the dataset. This process aims to ensure that the dataset does not disproportionately represent any group over others based on sensitive attributes, such as race, gender, or age. This step is important because AI models can inherit and even amplify existing biases in the data, leading to unfair or ethically problematic outcomes. Balancing the dataset helps in promoting fairness and reducing the risk of bias in the models trained on this data. Environmental impact of training neural networks. The environmental impact of training neural networks is significant due to the substantial computational resources required. These computations, especially for large models like those used in deep learning, consume a significant amount of electricity, much of which is generated from non-renewable sources. This, in turn, contributes to carbon emissions, a leading driver of climate change. Monitoring and estimating the carbon footprint of training neural networks is crucial. The provided code snippet defines a function, estimate emissions, which calculates the estimated CO2 emissions based on the amount of energy in kilowatt-hours used for training a neural network, and an emission factor that represents the kilograms of CO2 produced per kilowatt-hour of electricity consumed. The emission factor can vary depending on the regional electricity mix, and is here set to a global average of 0.475 kilograms CO2 per kilowatt-hour as a default parameter. This function helps in quantitatively assessing the environmental impact of neural network training by translating energy consumption into greenhouse gas emissions, thus enabling researchers and practitioners to make informed decisions regarding the sustainability of their AI projects. The future of neural networks and AI. As we look towards the future, neural networks and AI are expected to become even more integrated into our daily lives, transforming sectors like healthcare, finance, and transportation. Understanding the potential advancements and ethical considerations is crucial. Here, we will simulate a simple projection of AI growth using Python, highlighting the exponential progress in computational power and the increase in data availability. The code snippet provides a basic simulation of the projected growth of AI capabilities over the next decade, from 2021 to 2030. We use NumPy for numerical calculations and Matplotlib for plotting. The years array stores each year in the range. AI growth is calculated using a simple exponential function to model growth, assuming the growth factor increases exponentially over time. This is a hypothetical scenario meant to illustrate the concept of rapid progress in AI and neural networks. Finally, we plot this growth using Matplotlib, which visually emphasizes the exponential increase and its potential implications for various sectors. This exercise underscores the importance of understanding and preparing for the ethical and societal changes that such growth may entail. Neural networks in industry and research. Neural networks are at the forefront of advancements in both industry and research, spearheading innovation in sectors such as healthcare, finance, and autonomous vehicles. This code example demonstrates how to implement a simple neural network using TensorFlow, a popular framework used for both research and industrial applications. This code snippet is a basic example of creating a neural network model using TensorFlow. It begins by importing the necessary TensorFlow module and its layers submodule. The model is defined as a sequential model, indicating the layers are in sequence. It comprises 3 layers, 2 dense, fully connected layers with 64 neurons each, using ReLU, rectified linear unit, as the activation function, followed by an output layer with 10 neurons corresponding to the number of output classes, using the softmax activation function for multi-class classification. The model is then compiled with the Adam optimizer, which is a popular choice for neural networks, and the loss function is set to categorical cross-entropy, suitable for classification tasks where the outputs are mutually exclusive. Metrics for evaluating the model performance during training and testing are set to accuracy. This code represents a foundational approach to neural network design in TensorFlow, relevant across many applications in both industry and research settings.